My name's Kevin Duke, and I'm an analog applications engineer here at Texas Instruments. Today, we're going to talk about how to choose a precision DAC. Whether you're a novice engineer or an experienced engineer who just hasn't used a DAC before, it can be a very confusing process. We'll start off by talking about some of the less clear specifications. Offset error and zero code error are two very similar specifications for a DAC that can be easily confused. Offset error describes an offset or a shift in the entire transfer function across the linear region of operation. Think of it as the b term in y equals mx plus b. Offset error is calculated based on a line of best fit taken from a 2-point measurement across the linear region of operation, typically somewhere between 10% and 90% full-scale range to avoid operating the output amplifier in a potentially nonlinear region. Zero code error is also attributed to the output amplifier. It is the error caused by the output amplifier's headroom requirements near the positive and negative rails. It is measured by loading all zeros into the DAC data register and observing the difference between the output voltage and the ideal output voltage. Multiplying DACs, or MDACs, typically do not provide a zero code error or offset error term in their datasheets. This is because on their own, these devices are just resistor ladders that do not have an offset error term. Once the MDAC is paired with an amplifier, the amplifier will introduce an offset error term. In place of zero code error, the MDAC will usually provide a leakage current specification that describes the current that leaks to its output, I-out, when all zeros are loaded into the DAC data register. The next specification to consider is gain error. If offset error is the b term in y equals mx plus b, then gain error can be considered the m term. Gain error describes the deviation from the ideal slope of the transfer function, defined as 1 LSB. Similar to offset error, this is based on a line of best fit taken from a 2-point measurement on the DAC output near 10% and 90% full-scale range. Gain error is present in all precision DAC architectures. For an ideal DAC, any two sequential DAC codes should be exactly 1 LSB apart. Differential nonlinearity measures the worst-case deviation any two sequential codes actually exhibit across the transfer function. DNL could be specified across each and every DAC code, and there's usually a graph included in the datasheet that shows this, but in the electrical characteristics table, we simply show the worst case as a typical value and a maximum value. DNL is directly applicable to monotonicity and missing codes. If DNL at any given transition is less than -1, the DAC is referred to as non-monotonic, meaning there is a chance that increasing the DAC code will actually decrease the DAC output. If DNL at any transition were greater than 1, it may mean that the DAC has missing codes. Most modern DACs are monotonic and have no missing codes, but you should always double-check in the datasheet. Integral nonlinearity is very similar to differential nonlinearity, except rather than a code-to-code measurement, INL is the integration of all DNL measurements. Think of it as the result of all DNL errors stacked up on top of one another. In the graphic on this slide, the first region of the transfer function may be the result of sequential positive DNL errors. Meanwhile, the second region of the transfer function is the result of sequential negative DNL errors. INL describes exactly how linear the linear region of operation of a DAC really is. Finally, it should be noted that INL is corrected for offset and gain error. Total unadjusted error is a way of describing overall accuracy the DAC is able to achieve. TUE will take into account offset error, gain error, and INL error, all of the key flaws in the DAC DC transfer function. In many cases, these values will dominate the total error of the system, as filtering is typically in place to remove noise later in the signal chain. The reference voltage, of course, plays a tremendous role in determining overall system accuracy, but for this generic case, we'll only focus on errors intrinsic to the DAC. Using the DAC 8562 as an example, we can run through an example total unadjusted error calculation. The figures shown in this slide are the max error specs for INL error, gain error, and offset error. If we apply our root sum squared technique, we can calculate a total unadjusted error of 111 LSBs, 8.5 millivolts, or 0.17% full-scale range. Using the typical values for these specifications, our TUE is only 23 LSBs, 1.78 millivolts, or 0.0356% full-scale range. INL errors are primarily related to the resistor mismatches in the DAC ladder or DAC string itself. Since these are internal to the device, there is little we can do to calibrate them out of the system, but it is very easy to apply digital techniques to correct the offset and gain error of a DAC. The DAC 8718 even features this correction engine on silicon. The first step is to use a 2-point calibration measurement across 10% full-scale range and 90% full-scale range to avoid any impact of the nonlinear output buffer. Using these 2 data points, we can generate a line of best fit and calculate the offset error in LSBs from 0 volts at the zero code crossing. This term may be positive or negative and will be added to the adjusted code. Next, using the data from the same 2-point measurement, we can apply a gain correction coefficient to correct the DAC gain error. Digital calibration certainly has its limitations since we only have a finite set of codes to use, but it can lend itself to greatly improved performance when applicable without adding the cost of analog calibration. So with the specifications that we just discussed in mind, we can go to the TI website under Products, Data Converters, Precision DAC, and view the TI parametric search tool that can help us select a DAC. You'll see that this parametric search tool displays all of the same specifications that we just got done discussing, such as I and L. The parametric search tool also offers number of channels and resolution. If we click the Add or Hide Parameters button, we can add even more parameters such as zero code error, offset error, and architecture. So for a quick example, let's say we're looking for a 16-bit 2-channel DAC. By filtering just to a 16-bit 2-channel device, we've already eliminated from 213 parts down to just 8 parts. So let's choose the DAC 8562 for this example. At the DAC 8562 product page, we can view its datasheet, its IBIS model, and we see that the DAC 8562 has an evaluation module. And here we have the DAC 8562 evaluation module in hand. Precision DAC evaluation hardware and software enable you to quickly and easily evaluate a TI Precision DAC in your system or for your specific needs. The evaluation hardware features jumpers that allow you to configure the hardware options, a header to probe the analog signals, and a header to probe the digital signals. The DAC evaluation software DXP provides a quick method to communicate with the DAC without all of the effort of writing customized firmware. DXP allows you to write any code to the DAC, configure any of the DAC's registers, and even exercise more complex waveforms such as a sinusoid, a square wave, or a triangle wave. That covers all of the basics you should need to select a DAC for your own system. Remember the basic specifications, utilize our parametric search tool, and leverage our evaluation software to find the perfect device for your system. For more information, please visit the following URLs.